Welcome to Maths with Bob. Today we're looking at applications of calculus to the physical world, in particular projectile motion, and you can see here this is problem 3. Now this is a continuation of the series where we're kicking a soccer ball off the top of a building, and we're going to try and clear a flagpole 60 metres high and 40 metres from the base of the building. Now when I first did this question, I'll just show you what happened. Okay, I've got GeoGebra now. I just put the animation on, and I'm changing my angle now from basically 0 degrees to 90 degrees, and I'm kicking the soccer ball. And you can see I've marked the top there of the flagpole with top, and you can see basically I can't clear the top of the building. Okay, at 30 meters a second. Okay, and interestingly enough, and you can see I've got my velocity at 30 meters, and if I increase my velocity, I'll just go now. I just increase my velocity a little bit. Oops. Try and change my velocity up to say. Let's actually do it 40. And I think this is the one we're going to do. You can see here, if I actually change my velocity to 40, I can actually clear the top of this flagpole. So at 30 meters a second, when I kick the soccer ball, I can't actually clear the top, and when you set the equations up, you'll find that the discriminant will in fact be negative for 30, and there will be no solution. So we are going to have to increase, if you like, our speed at which we kick our soccer ball. Okay. Well, okay, you can see here I've just now changed my the velocity at which I'm kicking my soccer ball to 40 meters a second, because we couldn't actually make it at 30 meters a second. And we are now going to go through the equations and how we set up the quadratic for the angle. So the first thing is, let's actually have a quick look. So we normally do, obviously, as before, we always set this up. We know that, okay, y double dot is equal to minus 10, and x double dot equals 0. Then we integrate back one step to get y dot. Now you know y dot is equal to minus 10t, now plus the initial component of the velocity when time is equal to 0, which is just v sine alpha. In this case it's 40 sine alpha, so I'm going to sine alpha. Okay, the x dot is just the x component, and the velocity was 40 now, so it'll be just 40 cos alpha when t is equal to 0. Then we integrate again, okay, and we then get what y is equal to minus 5t squared plus, now it's 40t sine alpha, okay, plus the initial displacement of y, which was, as you know, 20 meters up on the building when we're kicking the soccer ball from. Okay, the initial displacement for x is just 0, so we then just end up getting a constant 0 here, which is just, what, 40 t cos alpha plus 0. Okay, well here we have the equations which govern the motion now, and we need to actually work out how we're going to find, if you like, these alpha angles, which are going to vary, obviously. And first up, obviously, we know the coordinates of the top of the flagpole, and that's what we're going to use in the x and the y equations to actually help us get this equation, or the quadratic equation in terms of alpha. Okay, so let's actually do that. Okay, here we have our equations, and let's actually just draw up a picture. I think always try to draw a picture. So what do we have here? Okay, we have a flagpole, top of the flagpole over here, the building, we're kicking the soccer ball, we've got to try and clear. Now, obviously there's a couple of angles we can actually do it at, okay, we can land in this couple of spots here. So, but what the important thing is that we know is the coordinates of the top of the flagpole, okay, and hopefully if you read the question, okay, this was what, 40, this was 60 up, so it's actually at 40, 60. So how do we use those, coordinates, I guess? Well, first thing is, we know these are the x and y coordinates, and we know we put them into the position equations. I hope we can see this, and then we can say, well, okay, let's have a look. If x is 40, then 40 is equal to t, or 40t, I should say, 40t you can see here 40 is equal to 40t, okay, cos alpha. Divide by 40, so 1 is equal to t cos alpha, okay, and t is equal to, if you like, 1 on cos alpha. Okay, so if you like, the time taken to get to the top of the flagpole is 1 on cos alpha, which we'll just write as sec alpha. Okay. So we're now going to have to substitute that into the y equation, okay, because we know that y is actually 60 there. So let's actually do that. We know that t is equal to sec alpha. Okay, so let's just do that. Okay, so we know t is equal to sec alpha. Okay, we get that t is equal to sec alpha. Therefore, the y position is, you can see here, 60. It's equal to minus 5. Now, t is sec alpha, so it's sec squared alpha. Okay, now we get 40 sine alpha times sec alpha, so 40 sine alpha sec alpha. Okay, still plus 20 here on the end. And let's move everything over. Okay, if we can just see here, we can, if we cross off 20, we end up getting a 40 here. Okay, and we can move everything over, so we end up with 5 6 squared alpha minus, now 40. Now sine alpha times sec alpha, hopefully we can see that it's sine on cos, which is actually just tan alpha. And the constant which we had is, what, 40. Okay, and that's equal to 0. Now we have to use sec squared as 1 plus tan squared, so we have to basically rewrite this as 5 lots of 1 plus tan squared alpha minus 40 tan alpha. Plus, okay, 40 is equal to 0. We end up getting what? 5 tan squared alpha minus 40 tan alpha plus 45 is equal to 0. And then we divide by 5 and end up getting, what do we get? Basically, what? Tan squared. So tan squared alpha minus 5 eighths of 48 tan alpha plus 9 is equal to 0. And this is a quadratic equation which we're going to now have to solve, okay, for tan alpha to give us, if you like, the two different angles which we're going to need to project, well, kick, if you like, to kick the ball from this position here, 0, 20, on the top of the building. Okay, so they all give us the two angles which allow us to clear that top of that flagpole. Okay, so let's actually now use the quadratic formula on this. Okay, let's now use the quadratic formula on this equation. So tan alpha, okay, tan alpha is equal to minus b, so it's 8 plus or minus the square root of b squared, which is minus 8 squared, 64, minus 4 times 1 times 9, you can see here, all over 2 times a, which is 1, 2. So we end up getting tan alpha is 8 plus or minus, now the square root of 64 minus 36, 28, okay, over 2. Okay, and we now will have a couple of angles for alpha. Okay, once we put that into the calculator, we'll end up getting, to the nearest minute. Okay, the two angles are 81 degrees 27 minutes, so therefore, okay, alpha is 81 degrees and 27 minutes. And also the other angle, when you put the minus 8 minus root 28 on 2, 53 degrees 33 minutes. 53 degrees 33 minutes. Okay, so these are the two angles, okay, and we're now going to have to try and work out where it lands. But let's actually just have a look at these two angles in our GeoGebra. Well, okay, you can see here I've set the angle at 1.42. This is in radians, and that's equivalent to about 81 degrees 27 minutes. Okay, you can see it just clears the top. And the other angle, 53 degrees, is about 0.93 radians. So if I drop it back to about 0.93, we are down to 1, 0.8. Okay, you can see here at 0.93 we're just clearing the top of the building. And you can actually just see we're landing around over here, about nearly 170 metres from the building. Okay, so we have to find those distances yet. Okay, let's go back to the problem. Well, okay, we're now going to try and work out the second part of the question, and you can see that's going to be where the ball actually hits the ground. let's actually put some red circles around the positions. Here they've got purple around them at the moment, but we need to actually find, if you like, the x positions of where the ball lands. Now, how would we do that? Well, if you have a look, what is the x position? Okay, well, you can see there that it's 40t cos alpha. Now, 40t cos alpha. We know the alpha, but we don't know the time. So we're going to need to find a time when the balls land, basically. And what do we know? Well, we know that y is equal to minus 5t squared plus 40t sine alpha plus 20, and we know its y position is actually 0. So that's going to give us a quadratic equation to solve, basically. So let's actually have a look at that. Okay, so let's actually now try and solve that. So we know what 0 will be equal to, okay, its y position is 0 when the ball lands, right? Okay, minus 5t squared plus 40t sine alpha plus 20. Now we divide by, okay, just divide by, say 5, yes, 5 goes into everything. Okay, so let's have a look. Minus t squared plus 5 eighths of 40. Okay, and 5 fours of 20. And that's equal to 0. Now I normally put everything over, if you like, on the left-hand side, make the t squared coefficient positive. So t squared minus 8t sine alpha minus, or actually, okay, so it's going to be put the other side, isn't it? It's going to be minus 4 is equal to 0. Now, okay, what is t? Well, a couple of things. T is going to equal what? Minus b. And what is b? Well, you can see it's actually minus 8 sine alpha. So it's actually going to be minus 8 sine alpha. So it's going to be 8 sine alpha plus or minus the square root of, now, okay, 8 sine alpha squared is 64. Okay, sine squared alpha. Now, minus 4 times a times c. A is 1, c is minus 4. So it says 4 4s are 16, plus 16, all over, okay, now 2a, 2 times 1, 2. Okay, so that is the time equation. And we do have a couple of angles. And we need time to be positive, so we probably won't use the negative square root. So we need to put in the two angles. Now, what were the two angles? You might remember the two angles are about 81 degrees 27 minutes and 53 degrees 33 minutes. So we need to substitute those in and get the times. So let's actually just do that. I've actually done it on a calculator, and I'm going to use the exact values for the angles. Okay. So let's actually have a look. So, okay, so what happened here? Okay, this particular position, okay, the angle alpha was actually equal to what? 87 degrees. 81 degrees 27 minutes. Sorry, it's 80. Okay, so it's actually 81 degrees 27 minutes. Okay. And how about this other one? Okay, this one had an alpha, okay, was 53 degrees 33 minutes. These are actually just rounded off to the nearest minute. Okay, so these are actually approximate. And I'm going to use the exact values in the calculator from the previous part of the question. So when I put those into that quadratic equation, I'm going to get some times. Okay, these are going to give me some times. Now, the time, okay, of flight, I guess you could say, until the ball hits the ground. And the times are roughly 8.39 seconds. Okay, so this one is 8.39 seconds. Okay, and the other one is actually 7.01. Now, these are just rounded off as well. 7.01 seconds. So I'm going to use the exact values on the calculator. Now, once I put those in, what do I put them into? Well, if you have a look, I'm going to need this alpha, okay, over here, into there, and this time, okay, into here. Okay, and then we just work out our x positions. So that's going to give us some x positions. Now, what are these x positions? Well, okay, after we substitute the angles and the time into the x position, we'll end up getting obviously our displacements on the ground there. And this one, the first one is x is equal to about 49.92 meters. It's 2 dp. And if you have a quick look down here, okay, this should be about roughly 50 meters here. So it's about, say, 50 meters where that one lands. That's the steeper angle. And the other angle, 53 degrees 33 minutes, and the time of 7.01 seconds. Okay, will give us you can see here, displacement x. It's about 166.48 meters. Going to 2 decimal places. Okay, you can see that's landing down here at about, say, 166 down here. Okay. Okay, so you can see we now have the displacements. Okay, so we're going to now move into GeoGebra and just to have a quick look at this. Okay, well, here we have GeoGebra. I've just graphed this at velocity 40 meters a second. You can see here just clearing the top. Okay, the top's over here. You can just see here. It just clears the top. Now, where does it land? Well, you can see it lands over here. Okay. And our calculations told us that was about, if you like, 166 meters. Okay, so I'm now going to try and change my angle now back to, I think it was about, no, you have to be careful, this is radians, so it was actually about 1.4 or something, I think, from memory. I just want to do the calculations. About 1.42, I think. Okay, I can get that to 4.2. Okay, all right. So you can see the other position, okay, is here. Now you might remember, oops, let me just try and get that to the right pin. Okay, if you have a look here, that was roughly about 50 meters. You can see here, there are the two positions for those two particular angles to clear the top of that flagpole. Okay, and that's where our soccer ball has landed. Okay, all right, well, thank you for watching, and bye for now.